Welcome back to From Brute to Best. This channel is built for one purpose: to help you transform the way you think about problems, not by memorizing patterns, not by copying solutions, but by understanding structure deeply and clearly. If you're preparing for coding interviews, especially trees and graphs, this video is going to change how you approach them. This is not a quick trick video, this is a structured masterclass, so slow down, grab a notebook if you like, open your IDE if you want to code along, and let's move from brute thinking to best thinking. Most candidates don't fail tree questions because they don't know the syntax. They fail because they don't understand the structure. And in interviews, structure is everything. In this video, I'm going to walk you through 4 of the most common binary tree mistakes that quietly destroy otherwise strong candidates. Not surface level mistakes, but thinking mistakes. And we're going to fix them properly using Java with clean structure, clear reasoning, and real interview level implementation. No shortcuts, no memorized tricks, just clarity. This is not a quick problem solving video. This is a deep master class on how to think about trees correctly. By the end of this video, you will understand why level order traversal is more about control than coding, know 2 clean approaches to lowest common ancestor and where to use each. Stop confusing height with diameter, and finally understand what recursion is actually doing in memory. If you're preparing for coding interviews, especially for product-based companies, this is foundational. So, take your time with this, pause when needed, and let's move from brute solutions to structured thinking. Most people think they understand level order traversal. They don't. Let's start with the first mistake, the one that looks harmless, but quietly destroys structure. Here's a simple binary tree. If I perform BFS and print nodes one by one, I might get something like 1, 2, 3, 4, 5. And many candidates say, yes, that's level order, but it isn't. Level order does not mean printing nodes in BFS sequence, it means grouping nodes level by level. Structure matters. Level order traversal is not just about using a queue, it's about controlling the queue. If you don't control the queue size at each level, you lose level boundaries, and the moment you lose boundaries, you lose structure. If this feels simple, that's exactly why it's dangerous. Let's step into Java and see what actually goes wrong.
To save some time, I have already created this class and an inner class tree node. So like my previous videos, I will not use simple list. I will create node class which will have a value and left and right node reference, and that I will use for entire throughout entire program for example. Okay, so now let me quickly start the coding for level order. Okay, so let me have a method here. Since it's level order, so it will return the elements at each level. That means it will be a list of lists, right? Okay, and now it will take input as tree node. Let me call it root node. Okay, now let me define a result. New array list. So here I will just add a base case here, or just a simple check that if root is null. Okay, just some validation. So I will simply return an empty list, right? Okay, now let me as initialize a queue of tree node. Okay, this queue will basically hold the elements at each level. Okay, so new linked list, and for the first element I will add our root node here. Now while the queue is not empty, so we will traverse through all the elements till the queue is empty, right? I will just first find the size of the queue, then I will have all the elements, right? So list of integers, okay. Now finally I will loop through all the elements of the queue, right? Sorry. So I will have node is equals to queue dot whole, and on level I will add this element when finally I will check if dot left has any element or not. So if left is not null, I will add that element in the queue. Similarly, I will also check if it has right element or not. Okay. So if it present, I will simply add in the queue. Okay. So that's it for our for now. In our result, we will add this level value. Sorry, add level. Okay. After while loop, we will simply return our result. Okay. So, okay, I think I missed a semicolon here. Yeah, so this is our simple code for level order traversing. Okay, now let me add a main method from where I will call this method. Okay, so inside main method, I'm going to define my tree. So my tree will be look like something like this. Okay, just a second. So it will be something like this. It will have 2 and 3, and then 2 also have some node, that is 4 and 5. So I will create a tree with this visual which will resemble this visual, and we will perform all the operations on that tree. Okay, so let me quickly create the tree graph which I have shown here. Okay, so tree node, first we will have a root node, so new tree node value will be 1, right? Next, root dot left will be new, sorry, new tree node value will be 2, then root dot right, again new tree node value will be 3, then root dot left will be new tree node which value will be 4, and finally root dot left dot right is again a node which value will be 5. Okay, so this tree structure which we have created will be something like this. 1 will be the root node having two childs 2 and 3, and 2 will again have two childs 4 and 5. Right, now let me add some sysout just for printing the messages. Okay, so level order, right? So level order where we need to pass root node, so root. Okay, so let me quickly run this code. Okay, here as you can see it has printed all the nodes of the tree with the level. So level 1 root node has only one element, I mean it will always be 1. Then level 2 we have 2 and 3, and on level 3 we have 4 and 5. Right, now let me quickly show you one edge case as well. So for example it will be a edge case where the root node or the tree will be empty. Okay, so let me write it here, empty tree. Okay, so empty tree, let me copy this out, level order empty tree, just to distinguish between the messages. Okay, and level order here I will simply pass null. Right, now if I run this, so you can see automatically the case we added here, that if root is null it will return the empty result. Right, so that's what it's done.
In the naive implementation, we use a queue, and while it's not empty, we keep polling nodes and adding children. That prints nodes in BFS order, but it does not separate levels. The missing piece is this: we must capture the current queue size before processing a level. That size tells us how many nodes belong to the current level. Without freezing that size, we mix levels together. Notice something important. The code didn't become smarter, it became more structured. Queue size controls structure. If you remove that single idea, your traversal is incomplete. So mistake number 1 is not about BFS. It's about ignoring structural boundaries. If mistake 1 was about structure, mistake 2 is about depth, and depth in trees is everything. Let's talk about lowest common ancestor. Suppose we want the LCA of two nodes. Many candidates immediately jump into recursion, or they store parent pointers and move both nodes upward. And sometimes it works until it doesn't. Here's the problem. What if one node is deeper than the other? If you move both upward at the same time, you're misaligned. You're comparing nodes at different levels. That's structurally incorrect. Depth is not a detail, depth is the design. So how do we fix it? First, compute the depth of both nodes, then move the deeper node up until both nodes are at the same level. Only then start moving both upward together. This alignment step is critical. If the visual explanation feels clean, good. But interviews don't stop at intuition. They test implementation.
Okay, so we will use the same class here. I don't want to create multiple class, and also since I will use the same tree, that's why I'm using same class. So let me quickly write the method. So to calculate the LCA, I will use to calculate the LCA properly, I will use recursion. So, and I will definitely help you to understand how the recursion is working. Just be with me while I'm completing the code. Okay, so this will be our method to find LCA value, and it will accept three parameters. One is the root node, then second is the number one, I mean two nodes, so node 1 and node 2, between which we need to find the LCA, right? So node 1, node 2, and since I will use recursion, I will first add the base condition. So base condition will be if root equals to null, that means for some reason I am getting a null root, or I mean the next call there were no child, so in that case, secondly, if root is equals to our node 1 or root is equals to node, in all three cases we will simply return the root. Okay, now using recursion I will find the left ancestors of the row n1. So I will again call this same method, but this time we will change the root with the left child, and n1 and n2 will remain same. Similarly, we will also find the right ancestor. Sorry, this time we will pass the right element of the current root, and n1 and n2 will again remain same. Now finally, once we got the left and right ancestor, we will check if left and right both ancestors are not null. That means the current root is the LCA value. Okay, we don't need braces here. We will simply return the root. Okay, else we will return whichever node, whichever ancestor has some value. So if left has value, so I will return left, or I will return right. So this is our simple code which will find the LCA between two given nodes. Okay, now let me quickly write some sysouts. Okay, let me add a comment here. This is for mistake number 2, LCA. Okay, so I need to find the LCA between 4 and 5. Okay, so I will simply write LCA between 4 and 5. Okay, I just need, so let me calculate the LCA. So we will start with the root, and n1 is 4, n2 is 5. So n1 is root dot left, and n2 is root dot left dot right. So we will pass that as it is, left dot left and root dot left dot right. Okay, and our expectation is it should return 2, node 2, as the LCA for 4 and 5. So let me print here LCA dot val. Right, now let me quickly run this code. Okay, yeah, so as you can see, it returned LCA of 4 and 5 as 2. Now how it worked, right? So let me quickly tell you how it worked. Okay, I will not show you all the stacks of this recursion. Just to help you understand, I will show few of them. Okay, so here is our root, then n1 and n2. Okay, and so for first iteration, our root is 1. Sorry, n1 is 4 and n2 is 5. Correct. Now on the second iteration, sorry, mm, this it will call root dot left. So root dot left will become 2. Correct. So it will goes for 2. This n1 and n2 always remains constant. So then, okay, so this, in this case also, this condition will, our edge case will not satisfy, sorry, base case will not satisfy, right? So it will call the next left value. Next left value is 4. So 4, 4 and 5. Now this time it will satisfy, the first second condition will satisfy root equals to n1, because root is 4 and n1 is also 4. So it will return me root. Root means it will return me 4. So here it returns here left became uh, left and right. So here left will become 4. Sorry, not here, here. So it will become 4. Now once this is done, it will call the, once it got some value on the left, it will call the right. Correct. So right will call with the current root. Current root is 2. So 2 dot right, it will call here, and here it will become, root will become 5, and this condition will satisfy. Correct. So this condition will satisfy, that means it will return 5, and automatically once it's returned, here the right will become 5. This will get cleared from the stack, right? So after finding both left and right, it will come here, this condition will satisfy, that left and right both are not null because both have values. So it will return me the root. Root is 2. So it will return 2. Again, if we check here, let's say, let me add one more value, that is result. Okay, result. So from this recursion, it will return 2 as result. So automatically this will get popped out, right? Let me add here. Let me remove it from here, and result will become 2. Now once result has received, uh, it on this no iteration, it got result automatically, right? So on this iteration, it will try to call the right again because it was all coming from left, as you can see, right? Now it will come here. So left is become 2 here, right? Left will also become 2. Now it will try to call with right. Right will not have any value. Correct. So right will have value. So for example, now root is 1, root dot right is 3. So it will come here. Let me note, write it down everything. Okay. So it will become 4, it will 5. Now 3, when it comes here, so it will again try to call 3 dot left. So 3 dot left will be null, right? So here it will be null. So null, the moment null will come, it will satisfy and it will return null. So for this iteration, left will become null. Okay. And again, when it try to come here, it will call with the I mean root dot right. So 3 dot right is again null. Again it will satisfy and it will return right as also null. Correct. So this will get popped out from the stack. Now the moment we come here, this condition will not satisfy because both are null. Okay. And what it will do, left is not null, it will not satisfy, so it will simply return null here. So at the end this will also get popped out, and at root level this will become null. Correct. Now coming here, this condition will not satisfy because both are not null, both are not null. 2 is not null but right is null. Then this comes here. Here it will check left is not null, so simply return left. So at the end, after this also, this iteration gets completed, the final result will be 2, and that's why it's printing 2. Okay, so I hope this example helps you understand this recursion code in much better way, right? Now let me quickly show you one edge case value. So for example, let me copy and paste this. Edge case is, let's say we need to find the LCA between node 2 and node 4. Here both nodes are not on same level. Also node 2 is an ancestor itself of node 4, correct? So it will automatically cover two edge cases. So let me calculate here. So root will be root, left will be root dot left, right? And right, n1 will be root dot left, n2 will be root dot left dot left. So here it will be left and it will be left dot left. Now let me change the message 2 and 4. Here also expectation is 2 only, right? So let me write down expected 2. Okay, for this case also expectation was 2. Now let me quickly run this code. Yeah, as you can see, 2 and 4, for LCA for 2 and 4 is also 2, right?
Recursive LCA. If the current root is null, return null. If it matches either node, return root. Then recursively search left and right. If both sides return non-null, current root is LCA. Otherwise, return whichever side is non-null. Notice something powerful. Recursion naturally handles depth. It searches bottom up. Alignment happens implicitly. If mistake 1 was about structure, mistake 2 was about depth. Now we move from local thinking to global thinking. And this next mistake exposes whether you truly understand recursion or whether you're just hoping it works. Here's a tree. If I ask you the height, you compute the longest downward path. But if I ask you the diameter, many candidates still compute height, and they feel confident. But diameter is not height. Height is the longest path from a node downward. Diameter is the longest path between any two nodes. That path might pass through the root, or it might not. The mistake happens when candidates compute height separately for every node, and inside each diameter call, they recompute height. That creates repeated work, and the time complexity silently becomes O of n squared. This works on small trees. It collapses on large ones.
Let me show you the correct approach in Java coding. Okay, so here I will write a method, or I would say I will use recursion again to find the diameter of a tree correctly. Okay, now since I will use recursion and diameter cannot be, I mean, should be a global variable because it's belongs to, it should go throughout the tree. So I will create a global variable diameter. Okay, so let me have diameter initialized with 0. Okay, Now let me create a method that will calculate the diameter. So it will also be a static method and it will return int like find diameter. Okay. Okay. Now let me, it will have the root node only, the only one node it needs to starts with, right? I mean, so it will just starts and then find the diameter. Okay, so just for, since it's a global variable, so just for safe side, let me reset diameter or reset diameter to 0. Okay, so I'm just resetting the diameter to 0. Then I can have here, but it will be recursion. So let me first create another method. Okay, that will be required to calculate the height. Okay, so calculate height. Okay, and it will also accept one node here. Since it will be a recursion, so I will first add the base case node equals to null. So I will simply return 0. Now int left, so I will calculate the left height first and it will simply goes with left node, and similarly I will calculate the right height, so and it will goes with right node, and at the end I will calculate diameter here with maximum value of existing diameter, I mean the current diameter and existing diameter, right? So existing diameter comma left plus right. Okay, and it will return, so here I will not return diameter, I will simply update the diameter, right? And at the end I will return the max between, sorry, left and right plus 1. Here I will call calculate height with the given node, and at the end after all the calculations I will simply return the diameter. So okay, so you may ask that what are we doing with this return value, because we are not capturing it in anywhere. So we can remove this, there's no issue, but since we had some int here, that's why we are returning. We can modify the method with void and cannot choose not to return anything, but that will again make our recursion fail, because base case, I mean since it will be void, so there will be no base case, right? So that's why I'm just added a return type with a base case and a return at the end of the method, but we don't need that return value because we are calculating diameter in that calculate height method itself, and it's a global variable, so we are at the end we are returning that diameter, calculated diameter. Okay, now let me quickly add some sysouts. Okay, uh, mistake 3, this is diameter of tree, right? So I will add sysouts, just system.out.println. Okay, some diameter. Okay, or not required because anyway it will be printed on next line. So I can say sound, and we will call our method find diameter with root. Okay, now the expectation. What's the expectation here? Correct. So expectation is diameter. I mean, with this tree, the diameter should be 1, 2, 3, right? So it will goes from 4 to 2, 2 to 1, 1 to 3. So it should return 3. Our expectation is 3 because it will go 4 to 2 to 1 to 3, right? So let me run this program. Yeah, so as you can see, diameter, calculated diameter is 3 for the given tree, right? Okay, let me also show you one edge case in the output. Okay, so edge case will be what if the tree is empty? Okay, so diameter of empty tree. So here we will pass, or not empty actually. Empty tree cannot have any diameter, but so we can pass null here, and what it will do, it will simply return 0. So let me show you that as well. Okay, so here I forgot to update the expected value. It will be 0, but the edge case I wanted to show you is different. I wanted to show you edge case with a single node tree. Okay, single node tree. So single node tree, here we can add, let's say, new tree node, any value, for example, let's say 10. Okay, so since it is a single node tree, so this also will not have any diameter because it's only one node. So here also our expectation is 0 only. So let us see. Yeah, so as you can see, diameter of single node tree is also 0, right? So
The correct approach is elegant. We compute height in a single traversal. At each node, we compute left height and right height. The diameter at that node is left plus right. We maintain a global variable to track maximum diameter. Height is returned upward. Diameter is updated globally. Height is local information, diameter is global information. If you mix those roles, you mix logic. If you separate them, the solution becomes clean. Now we've corrected structure, we've corrected depth, we've corrected local versus global thinking. But the final mistake is deeper. It's not about trees, it's about how you think about recursion. Recursion feels elegant, but it is not magic. It is stack frames. Every time a recursive method calls itself, Java creates a new stack frame. That frame holds local variables and execution state. If there's no proper base case, frames keep stacking. Eventually, you hit Stack Overflow error. When we compute height recursively, what actually happens?
okay, to demonstrate the use of base case, let me use an existing method only. Okay, existing recursion method. So for example, this calculate height, here also you are using recursion to find the height of the tree, right? So let me quickly change, since earlier we were not using the return value anywhere, so I just added some random code. but now let me first correct it. Okay, so it should be max. The height should be calculated with the max between I'm choosing the maximum of left and right, correct? Height should be the maximum level, not the minimum one. That's why I change it to max from min. Now let me add some sys out. Okay, mistake for recursion. Okay, let me first comment this diameter because it will also use the same recursion code, right? And if we remove the base case, the importance of base case, I just want you to understand. Now let me add some sys out here. The height of the tree. Okay, let me remove first height. We are not trying to make it grammatically correct. Okay, so height. Uh, calculate height with the root node, right? So now remember, I have removed the base case from the recursion method. Okay, now if I run this, what will happen? So it will go, cannot read left because node is null. Okay, why? Just a second. Yeah, so since we have removed base case, so this check is never happening, right? So it's trying to come here and trying to fetch node dot left. Okay, and it's throwing error. Anyway, it's not what I wanted to show you. Let me see if I can show you here. Okay. If I can make it this way, right? Node not equals to null, then node dot left, else node again. Okay, if I make this change and run it again, now see what's happening. It's going into an infinite loop and it's throwing Stack Overflow exception. Why? Because it doesn't have any base case, and also we made it deliberately incorrect, right? The code change we did. So now if I add the base case, so our code is correct. Let me uncomment this code as well because now it will also work. Okay, now if I rerun the program, see it calculated the height of the tree correctly, that is 3 by 3. So 1 2 3, height is 3, right? Let me show you one edge case also here. So for example, let's say we have a skewed tree. I hope you all are aware of what a skewed tree is. So skewed trees, I mean, so there's a difference between binary tree and skewed tree. Binary tree is a tree where any node can have at most only two childs, right? Left, I mean, no child, one child, or at max, at most two childs. Skewed trees, it can have only one child, and that too if it's left skewed, so only left childs, and if it's right skewed, only right childs. If you want to know more uh, about these different types of trees, please do let me know in the comment. I will make a separate or a dedicated video on describing or explaining different types of trees. Okay, for now let me just create a skewed tree here. Okay, so let me add preparing skewed tree. Okay, so tree node This will be skew root. Okay, skew root equals to new tree node value. Let me give one only, or we can give any value, 1 or 10 or whatever. Then skew root dot right. So I am preparing a right skew tree. Let me mention here. Okay, again new tree, let's say 12. Okay, then skew dot right dot right is equals to new tree node, let's say 14. Okay, and let me add one more value, which will be 16 right of right. Okay, so as you can see, I have only added child nodes on the right of each node. So that's why it's a right skewed tree. Okay, now if I try to find the height of this skewed tree, okay, height of the right skewed tree. Okay, so it's printed 4.
Space complexity in tree recursion is not always O of n, it is O of h, where h is the height of the tree. In a balanced tree, that's O of log n. In a skewed tree, that's O of n. If an interviewer asks for DFS space complexity, don't blindly say O of n. Say O of height. That answer shows maturity. Recursion is controlled stack growth. If you don't understand the stack, you don't understand recursion. Let's summarize. Mistake 1, not controlling structure in level order. Mistake 2, ignoring depth alignment in LCA. Mistake 3, confusing local height with global diameter. Mistake 4, treating recursion like magic instead of stack behavior. These are not syntax mistakes, they are structural thinking mistakes. Trees reward clarity, they punish guessing. If you made it this far, you didn't just watch a video, you trained your thinking. Tree problems don't test memory, they test whether you can see structure inside complexity. If this video changed how you think, then this channel is for you. We don't rush, we build foundations, we move from brute to best. I'll see you in the next one.